Hello, hello everyone. Um, this is Vander Nunes. I'm an assistant professor at SDSU, and welcome to the Crop Hour. This week we're talking about soils and water, and I'd like to introduce Dr. Jason Clark, SDSU extension specialist in soil fertility and assistant professor, as I mentioned. And today Jason's going to be talking a little bit about soil B, soil phosphorus. At the end of the presentation, we're going to be showing a QR code for those who would take credits. And if you have any questions, please raise your hand or write down questions in the chat. And that's it. Now it's all on you, Jason.
All right, thank you, Vander. I'll go ahead and we'll share my screen here. So today we're going to talk about soil phosphorus in corn and kind of the things we know in South Dakota and some of the research we've been doing the last few years looking at our recommendations. So first of all, I'll just kind of take a little bit of a bigger point of view. We have a picture here of a landscape, lots of different terraces and things like that. And when we're trying to think about soil phosphorus testing and also soil health and soil fertility, a lot of what I wanted to kind of think about, the bigger picture is a lot of what we're trying to do is really optimize the functionality, optimize our soil conditions. And we kind of look back at our soils 101 classes, we can kind of think more about what is that function of that soil. And some of the things that we learn in those classes, that soil is part of it. Its job is a hydrologic buffer. It also provides food, biodiversity, and habitat for crops and microbes. It's involved in nutrient cycling, has a filtering and buffering capacity for nutrients. Also, a lot of its job is to provide physical stability and support for plants, for crops, and things like that. And so really when we're talking about soil health is we want to look at a lot of this is the big picture, looking at all of these here and seeing how we can optimize these and get the best functionality of our soil. And kind of doing that, a lot of what we're doing is we're following soil health principles. These are some that NRCS puts out where we look at, are we arming the soil? Are we keeping residue or things on the soil to reduce erosion? Are we minimizing disturbance? So we're getting those macropores and those micropores where water can go through, where different insects and worms and other things can go through the soil and help with openings, help with aggregate stability, the structure of our soil, the movement of water. Are we putting different roots in the ground? Are we diversifying what we're growing so we can see different, so that we can see different roots in there to help and diversify those things? Are we keeping as many living roots in the system as long as we can throughout the year? And how well are we integrating livestock back into the situation? Are we able to do that? In certain situations we can. So we want another part of just look at how do these soil health principles affect soil? So we start to follow them. What are we looking for as far as changes go? We're looking at chemical things. We're looking at the pH buffering capacity of that soil. We're looking at how well it mineralizes nutrients. Is it retaining cations on the soil? Looking at physical properties, we're looking at greater aggregate stability, increased water holding capacity and infiltration. Looking at biological categories, we're looking at supporting a diverse and active microbial community. So we want them diverse, we want them active. And the bottom part for that, this last part, the biological one, is it goes into this next quote that I like from one of my mentors who shared with me, where it says, while the chemistry and physics of the soil system provides the context, it is the soil biota which is adaptive to changes in environment and circumstances. So a lot of times the chemistry and physics is the house that we put these microbes in, but they're the ones that adapt to the changing environment. They're the ones, whether it's a wet or dry year, cold or hot year, they're the ones that are adapting to whatever's going on. And that's what helps us be sustainable and consistent in a wet or dry year, or depending on what that rainfall pattern is or that temperature pattern is those microbes are adapting to what's going on and helping our crops and plants still grow well despite some of the environmental factors. So kind of thinking about this, that relationship between what's our management, what's our soil health, what's our crop growth, this is kind of one way I like to look at it. We're trying to look at changing some sort of management to improve the health of that soil. We want to see Does that soil health improve? And then subsequently, we want to see an increased productivity from those better conditions. And when we see that increased productivity, likely it's because the microbes are healthier, the soil is functioning better. We can see that soil health improvement. So we get a cycle there. The hope is then, well, this management change helps. So can I do something else on top of this to continue helping to improve that soil, continuing to go through this cycle of soil health improvement, increasing productivity from better conditions, and kind of continuing this cycle that we see here. So that's kind of the bigger picture thing I like to look at as far as when we're trying to look at management changes in soil health and fertility. Kind of some of the examples that we're thinking about is we wanted something that we could see as far as increased productivity. If we look at our crop yield from low to high and our nutrient input from low to high, we typically see a curve like that we're going to see here. We're going to look at an example of what a potential high soil health versus low soil health. So we want to see differences in as far as that functionality of that soil. We're hoping to see that increase in yield or that decrease in nutrient requirement from when we're making these changes. So when we're also thinking about is like, so what management changes, what are we talking about with these different soil health aspects? Well, some of them could be tillage. We could be moving from a conventional till system to a strip till to no-till, kind of to reducing that tillage aspect. We also could be look at, can we diversify our crop rotation? Can we add crop cover crops into that mix? Can we add, we said earlier, can we add a different cover crop? Can we add a perennial? Can we add sunflower? Can we add a small grain? Is there a new crop that's on the market that could potentially go in there? What's something else we can do to help diversify the crops and diversify the roots that are in the soil? So those are some of the management changes. A lot of those management changes are affecting these principles here as we minimize our disturbance, as we get more living roots in the ground, as we diversify those crops. And we're helping to hopefully help improve that soil health and increase those productivity conditions over here. So how do we know we're making a difference? That's the biggest question. I started doing this. Am I making a difference? How am I going to know? Well, we got to be able to measure it. We got to be able to look at something or measure something in the soil to see how we're doing. And those come down to the three basic things that we're looking at. We're looking at chemical properties, physical and biological properties of the soil, as well as crop growth. We're going to focus on the soil today. And these are the things we talked about, mentioned a little bit already. We have our chemical. We see lots of different ones that we have here, the micronutrients, the P and K, the CEC. These are different things we can measure. We have our physical measurements that we have, the texture, the porosities, aggregations, infiltrations. Our biological measurements, these are newer, the respiration and some enzymes that help with nutrient cycling, organic matter, the nitrogen that's becoming available in the soil. These are all a lot of different things that we can measure chemically, physically, and biologically to see if they're changing when we start making some of these management changes. So one group did this in the Missouri region of the U.S., looking at these soil quality, soil health across different landscapes, and they use this what they call a SMAP score as a soil management assessment framework. And what it uses these things right here. It uses the physical score, biological score, and nutrient score, so fertility, and a chemical score. And you can see the individual measurements that they use as far as assessing this. And they take these together and then they combine them to look at a score out of 100. When we look at kind of their different things, they have their score right here out of 100, and we have our different cropping systems down here. Generally, we see the ones that are higher in this SMAP score are those systems that are perennial, then followed by annual cropping systems. So within each of these, we look at the perennial system. We see our cool season pastures and grasses tend to be here, then our warm season ones. Our focus on the cropping production is like, how can I maximize what I'm doing over here? Because perennial systems, we're not tilling. There's perennial systems, that optimal soil health. So we're really trying to get as close to here as we can. And we can see that some of these systems are pretty comparable to some of these annual cropping systems. So we look, what are these? We see this right here. We see our rotational diversity, our no-till, and our mulch till down here. So we're seeing these different aspects. And this next part, we're going to look at kind of the same data, but more of a continuum. We have our higher soil health, SNAP, nutrient fertility scores over here, and our lower ones over in this area. In our perennial systems, we already saw this, our cool warm season grasses, our pastures and forages, our hays, restored prairies. Then we look at the part where it's focused on are these annual cropping systems. We can see what's interesting to me is when we start doing no-till plus cover crop plus rotation, these are the ones that are doing the best. When we have all three of these things together, when we take one out, we tend to move down this continuum of just no-till plus rotation, tillage plus rotation, tillage plus monoculture is the lowest, and then adding manure a little bit better. So we see them as we add different no-till cover crop rotational diversity, we start to move up this continuum in this direction. So then we want to focus on what about nutrient management, what it is that we want to do here, what are we expecting? So when we're looking at different improved management practices and we want to see how that affects yield, how it affects fertilizer inputs, there's some things to kind of look for when we're seeing a low or for our yield versus our nutrient input. We have our typical curve here where we have an increase in yield with increase in nutrients, then we kind of level out. And what we're looking at potentially with improving some management aspects, we're saying, okay, we're going to increase that yield, but our nutrient requirement still stays about the same. Or another aspect is maybe we're not increasing our yield, but we're lowering our nutrient input for that same amount of yield. Last aspect, if we can get this is even better if we lower that nutrient input plus we increase our yield. I'm trying to figure out, can we optimize this or what type of these scenarios we're looking at for changes in our management to improve that soil fertility aspect of our soil. So what soil health practices are we following? What are we doing well in South Dakota? So some of the things we're seeing tillage management practices that are changing. We're seeing a better use of our fertilizer, better use of our recommendations, and also an increase in soil health practices. So look at some of these specifically. If we look at our tillage management practice changes, you see in 2012, we're around 50% no-till, 23% conservation, 27% conventional tillage. We move that to 2017 to 2022. We can see that in tillage, we went from 48 to about 54%, about 5.8% increase in percentage of area that is no-till. If we look at our next ones here, we can see that we've increased from 23 to 29% in our conservation tillage and reduced our conventional from 27 down to 18 and 15%. You can see there that we are, we're moving from this conventional tillage to more of these areas of less tillage, hopefully helping with that, that soil health aspect of reducing the tillage and reducing the amount of times we're going through that soil. So when we're looking at fertilizer use efficiency, I like to look at, some of the 4 R's of nutrient management, that right source, that right rate, right time, the right place. How well are we doing with some of these things that we know right now? I know we're doing a lot of studies trying to figure out how to better improve these, but how well are these working? So when we look at this, we're talked to farmers a few years ago, about 83% of them were using university end rate recommendations, which is great. 60% of them are using an inhibitor when they apply nitrogen, or they're tilling within 24 hours to minimize ammonia loss because we want to keep it in the soil and not back up in the atmosphere after we apply it. So those are all good things. We look at our soil health practices that we already talked about. We see that we have about a 2 to 4% increase in the last 10 years where we're using cover cropping and increasing our plant diversity use. So not a huge increase, but we are seeing it's definitely a lot of management changes to add cover crops and increase our plant diversity. We're seeing a lot more of that, and we're trying to figure out how to best do that and economically do that as well. So again, we're kind of taking back this picture. We're looking at these management changes and how they affect soil health when we do these different aspects here. How do they affect phosphorus fertilizer management? It's kind of our big question today is when we start doing some of these, how does that affect phosphorus? Before we kind of focus more on specific studies, I want to look at and just kind of remind ourselves of how these crops are taking up nutrients and how a lot of what we're doing can potentially affect that nutrient uptake. So if we take our soils, if we're really looking at nutrient uptake, we can't really look at the surface. We've got to dig down a little bit deeper, and we've got to get to where those roots are, get to where those nutrients are located to really be able to see where they are and how we can improve our ability to capture those nutrients that are in the soil. Because we have a lot of nutrients and may just not be available. So we really need to see how well this rooting system can grow and really getting down to where that root surface is and seeing how well it's taking up nutrients and what it's doing to take it up. So we look here, we have our soil system, we have our root, we have our root hairs, we have our soil water, we have our soil particles and aggregates, and we have our air-filled pore spaces down in our soil system. So when we look at our nutrient uptake, we have our different nutrients that are on these soil surfaces and also in that soil water solution. And we have one of three ways we're taking up those nutrients. We're using mass flow, we're using diffusion, and root interception. So if we look at mass flow, this is where, these are the main nutrients here that we're seeing that are provided to the crop through mass flow. And mass flow really uses transpiration to create a water gradient. So it goes from a high water potential out here and to a low water potential here. And what that does is the plant is transpiring water, it moves water from here and it moves in. And as it does that, it's pulling these nutrients right here that are pretty typical, can be moved via mass flow, and it's pulling them in as it's transpiring, pulling water up and in the root and out. So that's mass flow. That's the most efficient. That's what we like to see. However, phosphorus, we notice it's not necessarily on this list. So phosphorus comes into play when we look at diffusion. That's our phosphorus and our potassium, and sometimes our iron, sulfur, and zinc over here. And what diffusion does is it moves via concentration gradient and goes from a high concentration to a low concentration. So the root kind of creates a low concentration gradient around it. So we get this movement from high concentration of nutrients to lower concentration to where it can. This isn't as efficient because it's just moving via concentration gradient in the soil. So it's not as efficient as mass flow. So then the question becomes, is there a way to increase this phosphorus uptake? Because we can't really get a lot of this farther away phosphorus. We can't create a strong enough gradient to get it pulled in. So one way we're looking at doing this is we also know one of the roles of arbuscular mycorrhizal fungi are to help with phosphorus uptake. Things that they help with are here. They dissolve phosphorus, they help with drought resistance, they involved in aggregate stability. And this one right here is those populations seem to be higher in no-till systems. And that's a lot of that is because these are mycorrhizal fungi. If you go, they reach out in the soil, but as they get cut off through tillage, then they have to grow back. So that takes more energy to do that. So these AMF populations are also helping to dissolve phosphorus. So if we look at how this arbuscular mycorrhizae can increase phosphorus uptake, what happens is these arbuscular mycorrhizae create these associations with the root, and then they go out and they can take up this phosphorus because they can reach out farther to help increase that area that phosphorus is available, can move via concentration gradient because it can reach out farther and explore more soil. And the root just says, I'll give you some, you can have a house in here, you can have some sugars, and I'll give you some food to help me get in that phosphorus. That's kind of what that does for us. Another way to look at that is if we have our corn plant here, we have our root system. It has this area right around here that it can explore, but we see there's a lot more phosphorus out here, and it'll take up that, but sometimes that's still not enough phosphorus. What that plant does, it says, you know what, mycorrhizal fungi, we're going to make an agreement, give you some sugars, give you some food, and you help me out, and you dig a little bit deeper out in the soil, expand that area that we can reach out into and increase that phosphorus uptake, help us, withstand that kind of that colder period where there's not as much phosphorus mineralized early in the season when it's wet, and also throughout the seasons because we expanded that area that we can reach out to. Another diagram showing this, we can see here as this root coming down, you can see that this is the depletion zone of that phosphorus. And then this is the phosphorus area. We can see that it can explore so much area of the root, around the root, but then we get these associations with mycorrhizal fungi. They can reach out and help expand that area that we're taking up phosphorus. So this is important. We're going to look at this with the Soil Health and Phosphorus project that we had in central South Dakota this last 10 or so years, where we focused on these two aspects of where we're minimizing disturbance and we are increasing our plant diversity. So we developed that study to see how it influences our phosphorus needs. So involving minimizing disturbance, it went from a conventional till system to a no-till system in 1990. For our plant diversity, it went from a corn soybean system, a little bit of wheat, to a 5-year rotation where we had soybean, followed by wheat and cover crop after the wheat or the small grain, back to soybean, and then 2 years of corn. So this is a 5-year stacked rotation that was started 5 to 10 years ago, or 10 or so years ago. And it's here in central South Dakota in Pierre, the Dakota Lakes Research Farm. It's an irrigated farm in this area. So we have no-till since 1990, 5-year diverse crop rotation. And then within this field, we established and maintained 3 soil test phosphorus levels. We have a low soil test, a medium, and a very high. The low and medium both have a 70 and a 50% chance of response to phosphorus. That typically says when we add phosphorus, you're likely going to see a response to phosphorus. So there's a very high one. The likelihood of seeing a response is less than 20, so we don't normally see fertilizer recommended. This usually yields as high as we can, regardless of how much phosphorus fertilization we apply. So we're typically what we'd expect to see in normal circumstances is these two would respond to phosphorus application. This one will likely not. So when we look at these, when compare these groups, we have our yield on our y-axis here, and we have our different years with our different crops on our x-axis. So looking at our 2018 soybean year, we have our low soil test phosphorus that's yield around 52, our medium right there with it, and our high soil test right there with it as well. So so we have 5 replications at the site. These boxes represent 50% of the data. The whiskers out here represent any potential outliers. We see most of the points you can see right here. Most of these points are within this box, and we can see there's a little bit of variability, but overall we're right here, no real difference, no statistical difference between these 3 treatments, even though we would expect a yield increase. So we do add a little bit of starter phosphorus to these soils each year to kind of maintain these 3 soil test phosphorus levels. So we're not just depleting them through removal of the grain. But we can see there's no real response, no difference in response to these different phosphorus levels, even though these 2 right here should likely respond to phosphorus fertilization. In 2019, for our wheat crop, similar story, regardless of soil test phosphorus level, same yielding levels as well here. In 2020, with our soybean crop, we see a little bit better yielding year than our 2018, but we still see the same level of yields for our soybean, regardless of that soil test phosphorus level. We look at our corn, we see a little bit more variability with our low treatment. However, that regardless of that soil test phosphorus level, we still see similar yields right through here, regardless of that soil test phosphorus level. 2022, we saw a little bit more variability starting to show up, but overall, we still see statistically there's a little bit of a difference, about 5 bushels less for the low yield. So if we were to add phosphorus fertilizer to this to make up this little bit of yield, we'd economically be losing money in this year. So we can see from here, typically across the last 5 years, we've seen no difference in the soybean and wheat crops, and very little to no difference in the corn crops as well, even though we have very different soil test phosphorus levels. So then the question becomes is what's happening in these lower soil testing phosphorus, the low and medium, they're yielding similar to this high. So one thing that might be is that item we already talked about is these arbuscular mycorrhizal fungi. Here we're looking at the number of propagules per gram of soil. So it's a measurement of the abundance of mycorrhizae in the soil. So in 2018, first we're going to look at our low soil test P level, our medium, and then our high in yellow. We can see that our low soil test phosphorus had a lot more mycorrhizal fungi compared to our medium and our high. And the same trend follows in 2019, 2020, 2021, 2022. And if we look across the 5-year average, we still see the same trend, where that low soil test phosphorus has a lot more mycorrhizal fungi in it compared to that medium and that high soil test phosphorus. So in theory, we don't see causation here because we're not changing these arbuscular mycorrhizal fungi numbers, but we can see the association with these lower soil test phosphorus is we tend to see higher amounts of our brassica mycorrhizal fungi compared to the medium and high soil test phosphorus levels. What might be happening in these is these are brassica mycorrhizal fungi are helping dissolve more phosphorus and get more phosphorus available in these lower soil testing soils to help make up the difference compared to those higher soil test phosphorus soils as well. So that could be one of the reasons we're seeing similar yields regardless of that soil test P level in this field. And this is also one field in central South Dakota. It's irrigated. It's been in no-till since 1990, diverse crop rotation. So it's also looking at that, and we're working on some other studies to see if this translates to other fields and other areas of the state as well. So just some conclusions, some summary. We're seeing that the long-term no-till with diverse rotation has the potential to increase the brassica mycorrhizal fungi. You can potentially reduce soil test P levels without yield reduction. And then has an increasing economics because we're lowering our phosphorus fertilizer that we need to optimize crop yield. So now we're going to transition from looking at the soil health recommendation to some general recommendations across South Dakota. So when we look at our current recommendations, typically we go out, we take soil samples, we send them to a lab, we get our soil test results back, and then from there we get recommendations of how much different nutrients to apply. So then when we look at our different soil measurements and making these decisions, we typically use these ones right here. We look at our micronutrients, our phosphorus levels, pH, CC, potassium, but typically right now we're just really using this phosphorus level to make our recommendation. So then the question becomes, is what additional tests can improve our fertilizer use decisions? Because we have a lot more out here. You can see a lot more tests, but they're not being used. So how can we use those, or can we? So these are 28 locations across 3 growing seasons. We've actually added to this. The stars are the different sites that we're looking at and having some different growers that have helped us. We also are continuing these studies. So if you're interested in having a fertility trial on your field, please feel free to contact me. My email will be at the end of the presentation. I work with farmers as much as I can to do things on their fields because the university only has 3 fields and we can't get this many different soil test levels in just 3 field locations that are along the eastern side of the state. So the more farmers I can get to help, the better we can get these recommendations and help make good decisions for our fertility programs. So if we look at these individual fields, what we try to do is we try to place different trials in different areas of the field that we suspect would have different phosphorus levels. We tried low-lying areas, up on hill slopes, on top of knolls, different areas like that. But within each of these areas, we have a control where we didn't add fertilizer, then we'd add phosphorus, we'd add potassium, and we'd add sulfur. And we'd look at the difference in yield when we didn't add phosphorus and then when we did, and what that relationship was with different soil tests. So when we look at each of these areas, we call them stamps. They're about 40 by 40 foot area in each field, and each one area. We took deep soil tests, we looked at the cores, we looked at the horizons, and we looked at the different soil profiles and some different parts of these as well. And then for soil fertility and soil health, we took a bunch of soil samples in that area, looked at our soil fertility measurements, our typical P and K, pH, CC, and then looked at several soil health measurements as well. So we also took plant sample or tissue samples around B7. A lot of times we typically see deficiency symptoms early on in the season as opposed to later in the season. So sometimes we want to test early on to see if this is make a difference early in the growing season. And then of course we did yield at the end of the year. So we're going to focus, we did a lot of different soil fertility and soil health tests. We're going to focus on just the use of soil test P first. So when we do these trials, we do them the way we showed you, but we also do rate response trials as well, where we have different rates for phosphorus going from 0 to 150 pounds. We replicate it 4 times in about an acre of the field, where the farmer doesn't apply phosphorus or we apply it in these rates. Then we get the yield data at the end of the year and we relate it to the phosphorus rate. So on this field right here is about 12 parts per million Olsen. the SDSU recommendation would be about 42 pounds of PTO5 for this field. So what we do is we see when we didn't add phosphorus, we got about 40 bushels per acre. Then we add phosphorus, that yield increases. So we needed about, our yield optimizes about right here, where we needed about 71 pounds of P, and we yield about 76 bushels per acre. This is kind of a central part of the state phosphorus response. So that's why it's a little bit lower yielding. But when we look at these things, we look at several different numbers on this response curve that when we work with farmers. One thing is we look at this 0 N rate, and that's our yield at 0, so that's 41 bushels per acre. The next thing we do is we look at yield, where we optimize yield, and that was about 76 bushels per acre. And then what we do is, so we can combine these across lots of different environments, is we do what we call a relative yield. So we'll take this number, 41, and divide it by 76. That's 0.54 or 54%. So we got 54% of our yield without applying phosphorus on a 12 part per million field. The other thing we look at is we look at the difference in yield when we add phosphorus versus we don't. That was 76 minus 41, is about 35 bushel per acre increase in this field by adding phosphorus. And what we do is we use all these different numbers to then come up with different recommendations and looking at correlations. What we do is we take that 12 part from this field right here, we take that 12 part per million on our soil test level, so about 12 parts per million. We go up, 54% relative yield is about right here. And then what we need to do is find out fields that have lower soil test phosphorus, look at their relative yields versus high soil test phosphorus and look at their relative yield. And from that, we can make a curve and see where we kind of level out. And once we level out, that's what's called the critical value. And in South Dakota right now, it's about 16 Olsen and about 21 Bray. We don't have this for Malick, which is why I really encourage farmers when they work with soil testing labs, have them do the Olsen test or the Bray test if your pH is below 7.4. If you're above that, use the Olsen test because we don't have that Malick calibration to tell you where that curve levels out. So when we look at actual data, what does this look like for our relative yield versus our Olsen soil test phosphorus? So here we can see we kind of have a scatter. We're below, this is 100% line. This is where we would, without fertilization, where we would no longer see increases from yield. So we want to see how it kind of starts down low and we start to kind of get up and stay around 100% over here. And there's lots of different lines, different math that you can use to try and figure out where that is, but that optimizes. The math isn't really the focus of this presentation, but to show you there's different ways to look at different numbers. And you can see these numbers vary anywhere from 20 parts per million to about 16. The average is around 17 part per million Olsen. So really close to our 16 part per million. So, and this also varies depending on what crop you are and also what soil test you're using. That last data I showed you was the Olsen phosphorus test. We're going to look at some different ones across the country now. This is the potassium test with soybean in Virginia, Maryland, North Carolina. We have a relative yield here. And this is Malick 1K as the extractant. So we're looking at potassium here. And we see this curve right here is a pretty sharp curve. We see it increase a lot and then kind of level off. We move to Arkansas and look at their soybean. This is now Malick 3 potassium. Oh, that critical value is 57. Look at Malick 3 potassium. We can see the increase, a little bit shallower increase until we kind of oftentimes about here, about 168 parts per million. And then if we look at Olsen P for corn in Iowa, Minnesota, and South Dakota, look at this data together, it's a lot shallower curve and similar to what we saw, the pretty big scattering. But if we do the data, we look at it, it's still around 16 parts per million where that critical value is located. So it kind of shows us, even over the years, where that 16 part per million Olsen is still accurate, even though it's been, we've done it the last 5 years. Ron Gilderman, my predecessor, did it while he was there and kind of found that same critical value. But also we need to understand that it really depends on which extractant you're using, whether you're using Olsen P or Bray P, Malick 3, Malick 1. Important to know that we have this data to know how to use this extractant. So for example, a lot of labs are running Malick 3 right now, but we don't have this correlation to tell you how to use that Malick 3 number. So it's best not to try and change that Malick 3 number and correlate it to an Olsen P or a Bray P. It's best to just leave it to have the lab run an Olsen or a Bray P, depending on your pH. So when we divide that data by soil test category, we have our less than 4 LSNP, or 4 to 8, 8 to 12, 12 to 16. And above that, this is kind of what we see when we say we have very low soil tests, or low or medium or high or very high. We're in these ranges right here, and we're above 16, which is, this is all just considered very high. And this is kind of that correlation responses that we would typically see. This is what's in your recommendation book. High chance of response at lower soil tests that decreases as we increase in soil test phosphorus. And this is also then we'd say fertilize until we get to this point right here when we're above that 16, that line right there. Once we get above 16, not high enough chance, not high enough yield change when we get above there. We'll show you the data behind that. So then we kind of look at the same data. We're going to look at these categories there, and this is that 100% line that we're kind of focused on. When do we kind of hit around there? So this is that 100% line. So we're less than 4, 4 to 8, 8 to 12, 12 to 16, 16 to 20, 20 to 24, and then greater than 24. So we can see, as we get these categories are slowly increasing. Then once we hit this purple category, that 16 to 20, we're kind of a little bit more. We still have some sites down here. We go above that, we're a lot more consistent. We still have some other random ones that are still responding. We'll talk about those in a minute. Another way to look at this is just kind of aggregate that data. These are box and whisker plots. I like them because it just shows the box is that 50% of our center data, the line is our median, the X is our mean. We kind of want to follow where does this kind of start to go up or hit that 100%. We see it kind of starting similar, 4 to 8, 8 to 12, around 90%. That 12 to 16, we start to get up about 95%, that mean value. And then once we're at 16 and 20, these lines are pretty similar to each other as we increase there. So just kind of another way to look at that same data, kind of grouping it a little bit differently as we go. But we can still see, where the 16 differences, we're pretty close to around that 100% data once we get above there. Another way to look at this is in kind of a yield response frequency critical value. This is where, just looking at the data a little differently, we're looking at yield response frequency. So if we did respond or we didn't respond, we had a 5% or a 5% or 5 bushel yield change, and we considered it responded. So our percent response versus our soil test P level from low to high. So this is the first one we're going to look at as percentage of raised. So if we increase our yield, it's the highest at low soil test phosphorus, and our soil test P increases, the likelihood of seeing a response decreases. So the percentage of time we see it goes down, which is pretty typical what we'd expect. Less likelihood of seeing a response at higher soil test P. Thing we don't really think about is if we're adding phosphorus, does it ever decrease yield? So the answer is yes, it can. So as we increase in soil test phosphorus, if we add phosphorus fertilizer, sometimes we can get to the point of decreasing yield. The caveat to this is that this study, because it was a regional study, we had one rate that we used. So this is adding 100 pounds of P. It's not adding just a replacement value of the P from the previous crop year. So it's not adding 30 pounds of P. This is adding 100 pounds. So what this is saying is, as we increase in soil test P, if we're adding another 100 pounds on there, we're increasing the chance we could be lowering it. And this is also a spring application. And what we typically see is what we think about is doesn't really change yield. That's what this one does, falls similar level. The interesting thing is that these two intersect about 20 parts per million Olsen, which is that 16 to 20 is what we'd say is kind of that critical value range of where we're not seeing a response. And also what this tells us is if you're around that 16 to 20 parts per million, don't add 100 pounds of P because you could decrease yield. You want to add a little bit of replacement, you're probably fine. So another way to look at this same data is we looked at other one, whether we see a response or not, this is the change in yield. I like this because sometimes it's a little bit more concrete to me rather than looking at a percentage of our yield. So here we're looking at kind of an average change in yield, and we're looking at the different soil test categories. So this is looking at, remember that graph, our optimal yield minus our 0N yield, our 0P yield. So we look at this from a high change in yield. This is our 0 line right here. Above it, we're increasing yield. Below it, we're decreasing yield. So this is kind of the trend that we see as we're at low soil test phosphorus. We have the most increase in yield when we add P, and that yield change decreases. We hit 0 around 22. The interesting thing is if we want to look at a 5 bushel yield increase, we're around that 16 parts per million Olsen, where we start to see that. So we look at these categories right here. We have our Olsen P categories. And kind of what the data is showing us is that similar to what we saw in the guidebook data, as we have lower soil test P, the likelihood of response is higher at lower soil test Ps. And as we increase, we see a lowering of response. If you notice, we're still around that 40-30% chance. This is only, we have about 50 sites within this data set. If we kind of increase that, we'll probably see these numbers change or decrease some. But we still see some response. But the question is how much is the response of these sites? So then we look at our relative yield of these sites. So we see that, as we increase in soil test P, we're increasing that relative yield like we saw earlier. It's these ones, sometimes the response, but the response is pretty low because our average yield is still around 99%. And this is the part that's interesting to me, is looking at that yield change. So this is the median yield change, kind of that middle value. And so we see as we are lower, we have a 16 bushel increase on average, 17, 13, then we start to decrease around 12 to 16, we're seeing an 8 bushel change. And once we go above that threshold, that 16 value, we really start to see, this goes down to like 2, 3, or 1. So yes, there's a chance of seeing response, but that yield change is pretty low. And so this is the median value. Okay, let's give it some differences. This is what we call a 25%, a 75% quantile. So it's the middle 50% of the data. So we kind of get rid of some of the extremes by looking at this. We see kind of the range in those low soil test categories of change in yield between 9 and 24, 9 and 29, at 3 to 4 for 8 to 12, 12 to 16 bushel or 12 to 16 part per million range, 2 to 18. Then as we get below or above that 16 part per million threshold, this line right here, we start to see the variability. We start to get into potential negatives. We start, seeing that extreme, our average is 2, 3, and 1. And then our extreme high, the best we can do is 23, 10, or 12. And this is, just 1 or 2 sites that did this. So we can see generally, we might see a response, but that response is going to be pretty small when we're above that 16 if it's there. So just kind of in summary, looking at this, that critical value we're still showing is around that 16 to 20 range. We want to do a confidence interval, 13 to 22 is where we kind of optimize out to give ourselves, looking at some of the variability in the data. We want to see a 5 bushel response around 16 part per million Olsen. But the accuracy of using this test by itself is about 68%. And the accuracy comes, or that error comes right here. That error comes when we're below that critical value, but we're not seeing a yield response. Right here, we're right at that 100% still, but we're below that critical value. And right here, we're above that critical value where we would say, it doesn't respond to phosphorus fertilization, but it still did. So to improve the recommendation, we're trying to figure out is, can we move these values over here to the non-responsive side because they didn't respond? And can we move these ones over here because they did respond? So what else is about it besides soil test P? Because soil test P alone told me to fertilize here, not fertilize here, but that wasn't correct. So what else about the soils do we need to know so we can make the correct decisions on these 2 groups as well? So that's really what we're looking at. Does this soil critical value change? Based on some of these systems, does it move to the left? If we have low soil health, does it move to the right? If we have higher soil health, things of that nature. So what variables improved our P recommendations? That's these ones right here. So we had our Olsen P stayed there. Soil respiration, this is a measurement of microbial activity. So how much they're respiring. So the higher the number, the more active they are. Our cation exchange capacity, and then our clay content. To kind of show how this goes out, we look at this and say, generally, if we look at our soil tests, our Olsen P level, when we're above 17, we typically say don't apply, but we saw some where we still responded. So what is it about those sites? And we still have a 32% chance of response. We follow that down to our cation exchange capacity. When we are above 19, there's only a 7% chance of response. So probably definitely don't respond there. If we're below 19, and our kinetic exchange capacity, we still have a chance of response. So that kinetic exchange capacity could explain some of those sites that we're seeing above that threshold but are still responding. So then if we look at the other end of the spectrum, when we're below 17, we typically would say, yes, you're going to respond. But we saw a lot of sites that didn't. So if we look then at saying, oh, well, look at your soil respiration level. When it's above 124, you only have a 49% chance response, but you also need to look at your clay content, because when it's below 55, which is most soils, you don't have that great of a chance of response. So if you have a low clay content soil and a higher soil respiration, when you're below 17, you're not likely going to see as much of a chance of response, even though we typically say it will respond. So that could be explaining some of the sites that are below that critical value but still responding. Because when we're above 55, we still have a high percent chance of responding. So we follows the trend when you're above 17 still see response. The other aspect of following this is looking at soil respiration. When we're below 124 and you're below 17, 80% chance instead of only a 61% chance. So we can see here, not only can we use Olsen P, but we can use our kinetic exchange capacity, we can use our clay content, we can use a biological soil test with soil respiration to help improve these recommendations. So what about adding soil health? We see 68% correct with Olsen P alone, and we increase that to 74% when we use Olsen P, soil respiration, kinetic exchange capacity, and clay content. And again, this is with the data that we have, and what we're doing now is we're going forward, we're trying to test this equation. So we're working with farmers to try and see, can we use these ones, focusing on these ones here? Can we use these ones with your field information to be able to improve the accuracy of the recommendation? So take home, including these biological and soil properties can improve our phosphorus recommendations. So that's kind of what we have today to focus on. I have a little bit, still have some time for questions. I wanted to leave some time there. This is my contact information. Please feel free to email me and ask questions about this. If you're interested in soil fertility trial, we have some slated for 2025. We have some nitrogen rate and timing studies, as well as some P and K rate and placement studies. For these studies, we're looking at K below 120. If we're below 150, we can potentially do it as well. Phosphorus, we'd like you to be about below that 12 part per million Olsen, 15 Bray. If you do Malic 3 color less than 17, Malic 3 ICP less than 27. So these are basically our medium. We don't want higher, very high testing soils. We want them more in that medium range so they're more responsive to fertilization. But if you do have a low and a higher soil test P levels that you want to try some things out in, that's also. So you have one field that's 12 and you have one field that's 17 or 18. You'd like to see, because you might still see some responses in that higher test field. I also like to do those comparisons. So if you have a high soil test P field and a low one, those are also interesting as well as on with K. But with that, I will stop sharing this.
Jason, there's a question from earlier in the talk. Can you provide a high-level definition of high soil health versus low soil health? And I think you mentioned some framework in quantifying it, but I think it kind of goes off of that.
Okay. So high soil health, that's what we're trying to figure out. That was just an example of, so this is what we're looking for. So a lot of what we're looking with soil health is we want to measure some sort of management change. So we can figure out if we're looking at, and that's one thing we're looking at. We get these soil health scores and we want to know, what do they mean? So that's kind of what this research is looking at, is can we use these soil health scores to help manage our phosphorus? And what is low soil health versus high soil health? That's what we're trying to figure out with these measurements, is what does soil respiration say? When are you at low soil health versus when are you at high soil health? That's what these things are kind of looking at. A lot of what we look at with soil health is looking at management practices that hopefully increase it, with those principles of keeping residue on your surface, the tillage parts, livestock, getting different cropping systems in there. So that's kind of what this is looking at, is, so what is high soil health? And that's what we're trying to figure out a lot of, is using some of those metrics to see if that management change is improving our productivity. So it's still kind of out there. It's kind of a half answer, but it's kind of out there. We're trying to figure out what is higher soil health and how does it affect it. If we do these soil health management practices, how does that affect our fertility? And that's what some of these things are trying to figure out.
I guess I sort of had a question about that because you were showing on what you were just showing that soils with higher respiration and higher CEC didn't respond as much to phosphorus. So wouldn't that be soils with higher organic matter and theoretically more biological activity going on?
Yeah, and that's some of what these things are indicating that probably should spend some more time. When we have our higher soil respiration measurement, that's likely a higher amount of microbial activity, which is hopefully helping with nutrient cycling and maybe why we didn't see a response when we typically would.
Well, thank you very much, Jason. I really appreciate it. If anyone have any other questions, as I mentioned, and you're going to receive an email about a survey. And yeah, thank you very much, Jason. The presentation was very, very interesting. I'm really glad to see that you're moving forward towards this position where you're not using only a p-test result, but also trying to incorporate several other soil properties, physical, chemical, and biological, to try to maximize P response. Very, very nice idea. Congrats.
Jason, there's a question for you in the chat. Are you guys doing any studies with hemp?
I have not done any studies with hemp with soil fertility, no.
Okay, well, the poll has ended, so thank you everybody for attending and hope to see you tomorrow when we return at 10 a.m.
Thank you, everyone.
Thank you, Jason. Bye-bye, everyone.